going to talk about, we're going to review this idea of vapor pressure, then we're going to move on to Clausius Clapeyron, and then I have something fun planned.
Is it a little long? Yeah.
Yeah.
Well, if you turn your attention to the right more.
That's Chem 1 lab.
We already talked about it. Oh, you're already
Yeah.
in labs.
See, I pinky promised that was in your lab.
You didn't pinky promise.
Wait, that's
I
our
didn't
lab?
believe- I didn't believe
That's not yours. That's this lab. This is for Chem 1.
Oh,
no.
Yeah.
What one was that?
I like that one, the neon.
Quantum, it's quantum. They're doing the quantum model right now.
You don't remember the
So,
balls and the discs?
I don't remember the balls in the disc, but I remember the light.
I remember the light, but I don't remember the bulb.
yeah.
We had
So
the-
you guys, we're going to talk about vapor pressure, then we're going to talk about Clausius Clapeyron, and then we're going to do a lab. Okay? So,
Yay.
Taking all that information and like.
yeah, I mean, it's Tuesday, right?
Let's
Oh,
try.
okay.
Never mind, we can try. Let's go.
Oh, yes, Friday.
There you go. I like the enthusiasm.
I'm surprised this morning already. It's been rough.
I know, it's been rough. It has been a rough day. Okay, so yes, the last time I saw you, whatever day that was, we talked about vapor pressure and how if we just have a liquid in a sealed container, this is, pretend that's completely sealed off, we're going to have some water molecules that have enough energy that they can escape into the gas phase. Because temperature is the average kinetic energy of the particles, so you're going to have some that have really low energy, you're going to have some that have really high energy, you're going to have the majority of those water molecules are going to be in the middle. So the ones that have the really high energy and can escape into the gas phase are going to do so. But some are going to have a lot of energy, they're going to come up here, they're going to collide with each other, they're going to transfer some of their energy, and it might cause them to come back into the liquid phase. And it's just going to be this constant back and forth. But what you're going to see is that those particles that are in the gas phase are going to generate a pressure. That pressure is from the vapor molecules in that closed container, and we refer to that as the vapor pressure. But if we would heat it, we would see that more of those molecules would have more energy because a higher temperature corresponds to a higher average kinetic energy. And you're going to see more of those particles are going to turn into the gas phase. And because there are more particles, they have more energy, they're moving around more, you're going to have a higher pressure. And that higher pressure is going to cause a higher vapor pressure. And this is where we start to see some containers that will, I don't know if you've ever seen like a can that has been out in the heat for a long period of time, it'll start to bloat.
Yeah.
So that's what happens when you have a really high vapor pressure. At some point, the container can fail, and when it fails, it explodes. So if we would cool this down and we would have a lower temperature, what would you expect to see compared to one at room temperature? Would you expect to see the same number of particles, fewer particles, more particles in the gas phase?
Oh.
Fewer. If we cooled it down, then fewer molecules have enough energy to escape into the gas phase, and the vapor pressure would drop. Okay? So, with that in mind, we know with the vapor pressures have been measured for all kinds of substances at 1 atmosphere pressure, that normal vapor pressure. But this is where I'm going to introduce the Clausius-Clapeyron equation, because it allows us to estimate what the vapor pressure would be at any temperature. If we know the vapor pressure at a temperature, we can estimate what it would be at any other temperature. I'm going to say that one more time. If we know the vapor pressure at a temperature, we can use this Clausius-Clapeyron equation to estimate the vapor pressure at any other temperature. Now, of course, there are a couple of conditions, or a couple of things we need to consider. I guess it's not conditions, a couple of things we need to consider. First, the temperatures have to be in Kelvin. Yeah. Because anytime we have a temperature as part of our fraction, if we have 0 degrees Celsius, what is that going to look like in fraction form? It doesn't make sense, right? It's undefined. So we want our temperatures to be in Kelvin. And R is the gas constant. R is the gas constant. remember your resource packets of fun from last year?
Yeah.
Yeah, so the gas constant should be in there. And you should also have in there the conversion from Celsius into Kelvin. So if you look at, it's one of the last pages in here. I think it's like the second or third to last page in here. There are gonna be the gas law equations. It says at the top, gas law equations. And in the middle, you have, down here towards the bottom, you have the gas constants in all their different forms. Now the one that we use is gonna be dictated by the pressure unit, but those are there. Okay, so temperature in Kelvin
Is that a one?
is this a one?
Like,
Yes.
all of them.
Yes.
Those are all ones. This is natural log, Ln.
Oh, okay. I
I
was
thought it said
mainly
N.
talking about that one, but yeah.
Yeah. This is Ln, this is the natural log of the fraction of pressure 1 divided by pressure 2, and that equals our enthalpy of vaporization.
What is Okay, I don't know if this is gonna sound weird. What is delta? Like,
Delta means change in.
so that isn't a number or anything?
This will be a number.
All of it?
The whole thing is one number.
Okay.
Yep. And then we divide by the gas constant, and then we're gonna multiply by 1 over T2 minus 1 over T1. Now I wanna point this out, so I want everybody to see. If the first pressure is on the top of our fraction, then we'll have the first, or the second temperature first. One more time. If the first pressure, the pressure in the first situation is on the top of our fraction, then when we put our temperatures in order, it's gotta be T2 minus T1. But you can flip it. This could be P2 over P1, and then this would be T1 over T2, but T1 and then T2 in the second spot. But they have to be in that order, okay? And I'm just gonna leave it at that. We'll see what happens when we work with natural logs. I feel like that's hairy at best. So that's the Clausius-Clapeyron equation. And there's some manipulation we can do with that. I'm gonna kind of leave it and see how that works out first. And that is the last slide that I have to show you.
I don't like that.
You know?
So, what
You
is
want
our-
more?
No.
What is our test over? Is it just over those equations that we were working on?
No. It'll include all of the intermolecular forces. It'll include all of the discussion. It'll include the calculations of unit cells. It'll include the Clausius-Clapeyron equation. But there's gonna be some questions where you have to like connect everything together. And we're not there yet. That's next Monday, right? Is today the 8th? I don't have the date on my phone. I don't know why I looked at my watch. I don't have the date on there.
Yes. Today's the 8th.
Okay, so that'll be next Monday. So we're gonna do this lab, and then we're gonna see if we can sort of connect everything together after we finish the lab. And I wanna give you a chance to work with the Clausius-Clapeyron equation a little bit. So, remember your unit cell paper with all
Yeah.
the problems on it?
Yeah.
Please take that out for me.
Oh, that was the stuff on the back, wasn't it?
It is.
Can I go grab that from my locker?
Yes, you may.
I grabbed the wrong folder.
Yes, you may.
I think I have 15,
Okay,
which isn't great for your video, so I'm sorry.
that's okay. Like, do you need to go now, or can you wait until we talk about the lab?
No, I think I'm good.
Okay, so what I also want you to do is I want you to go ahead and write the Clausius-Clapeyron equation in your packet, somewhere where you're gonna be able to find it, because I do not believe that it is there.
That's a problem.
Yeah,
I'll look for it.
so I should make a note to add that for future reference.
Where is it at?
It's not in there, so I want you to add it wherever you're gonna be able to find it. It's up to you where you wanna add it. I would probably add it to the gas laws page,
Yeah, I was about to say.
because it's a vapor pressure, it's related to all that stuff, the gas constant's right there. I'm gonna add it in mine while I'm thinking about it. Yeah, it'll be based on the pressure unit. The only difference between all the gas constants is the pressure unit. So, you'll have them right there. If it's all together, then hopefully that'll set you up for success. So we're adding, Courtney, the equation to your packet, your resource packet. And I suggest putting it on the gas laws equation page so that you have it right there beside the constants. But you can put it wherever you want as long as you know where it's at when you need to use it.
Okay.
All right, so that brings us to, ready? Wait for it, the lab. And it says, stations, but we're not really doing this in stations because we don't have to. This is a small class and it's the only one that I have, so I don't have to set up the stations.
This is your only Chem 2 class?
Yes, but I have to have 2 Chem 1 classes this year, which is really weird. So, I don't know how that's gonna work. But let's take a look at the lab. Comparing the strength of intermolecular forces. So, we've got some information here. I've got some samples in the back that I'll pull out here in just a moment. But I want you to make some really good observations. So for example, in the first table, it says results of swirling versus results of shaking. Like literally make observations about the bubbles, about the way that it moves, whatever observations that make them different, make sure you write that down. It's gonna ask you to look up a couple of structures. I would just draw them out nice and neat here. If you need to do this on a separate sheet of paper, that's absolutely fine. On the back, station 2, comparing molecules with only London dispersion forces. So if these only have London dispersion forces, then that means they only have London dispersion forces. Right? It tells you. Right? I feel like sometimes that stuff that you're told is overlooked. So it's going to ask for the state or phase of the sample. We're looking for solid, liquid, or gas. And then it's going to ask you to explain. There's not a whole lot here in this lab that you have to do, but you're going to be explaining a whole lot of stuff. On the next page, surface tension and strength of van der Waals forces. So I have oil and water. I'll get those out here in a moment. And wax paper. I'm just going to give everybody a little piece of wax paper, and you can look at the droplets, draw it, be very creative. Here's your opportunity to bring out those art skills that would make us all so proud. Evaporation and comparison of attraction between molecules. So I'm not actually going to have you, maybe, I have to see what I have. But you're basically going to wipe down the desks. The only thing I ask is that you make it very clear to me before you leave which desks you wipe down so I can spray them down when we're done. There's nothing in here that's going to harm anybody, the stuff that you're going to be wiping on the tables, but we want to make sure that we have a coating of the spray on them just in case. And then the last one, oh no, I lied, there are 2 more stations. The next station is viscosity.
You put it on your desk.
Yeah, I think so. On this desk?
I think so.
I don't know why I can't keep track.
How about it's this one that's right here?
Oh yeah.
She lied to us.
I said
Did
yes.
you see it?
I was thinking
Hannah
that.
lied to us.
Oh, good.
And I told them all that if they were not students of Clark State, that they needed to register like now.
Yep.
So, there you go. And, yeah, I'm feeling it. Okay, so then the next station is comparing viscosity. Now remember, viscosity is a resistance to flow. And that means that if we spin it, things with very high viscosities versus things with very low viscosities, there's going to be a difference in how they move. And then the last station on the back is intermolecular forces and evaporation lab. So you're going to use a damp paper towel, and you're going to use a wet wipe. And I'll get the wet wipes out, but you're not going to you don't need to like wipe down the whole table. I would recommend just like one little strip. And if you guys want to do this part together, like maybe you do the wet paper towel and you do the wet wipe, and you just kind of like put them down together and you look at them and compare which one evaporates the fastest. that way, you know, I don't have to spray down my entire room and floor and chairs and the walls and. Okay. Any questions? Do you have enough information to make you dangerous?
Oh, no.
I'm already
We're just going with it at this point.
All right, I like it. Just go with it. That's what we do in chemistry. All right, so let me